All right, so today we're going to be slowly wrapping up Chapter 7, and we're going to finish by talking about leaving groups. If we think about leaving groups, they're really important for one type of substitution reaction. Which substitution reaction are they very important for? SN1, right? We said in SN1 reactions, the leaving group falling off is the rate determining step. So let's make a note of that. Leaving groups are very important for SN1 reactions. Because the rate determining step, or the RDS, involves the leaving group falling off. The easier it is for that leaving group to fall off, the lower that activation energy is, the faster that SN1 reaction will occur. It is somewhat important for SN2 reactions, so let's make a note of that. So it's moderately important for SN2 reactions, but it's much, much, much more important for SN1 reactions. And the reason it's important for an SN2 reaction is that rate limiting step, that transition state, does involve the leaving group falling off, but it also involves the nucleophile. So it's got two important features. So we'll say leaving group falling off is not solely responsible, for rate determining step. The nucleophile matters. So now we've got to come up with some sort of system for comparing leaving groups and which one's a better leaving group, which one's a weaker leaving group. So let's make some educated guesses and we'll just do some comparisons. We'll do leaving group comparison. All right, we'll do iodoethane versus bromoethane. Which one do you think has a better leaving group? Iodomethane. Okay, so we'll circle this and we'll say this one's the better leaving group. Why do you guys think it's a better leaving group?
More stable.
Yeah, exactly. So we could say I minus is more stable than Br minus. Is that due to electronegativity or size? Yeah, due to size. All right, so that one's pretty easy. Let's try another one. This one's a little bit more complicated. First of all, let's try to circle the leaving groups in both, and then determine which one would be the better leaving group. Once you think you've got it, talk with your neighbor and see if you guys agree.
It is LR, yeah. It's an O.
I actually
All right, let's see thumbs up if you guys agree on which one has a better leaving group. A few. Let's kind of go back to the basics and first identify what the leaving group is on each of them before we identify which one's better. All right, just for the sake of argument, am I going to lose a methyl group? No, that would be a terrible leaving group. Methyl groups and hydrogens just simply don't act as leaving groups. They're not stable falling off on their own. So if we look at this, will this be our leaving group? Not quite. However, what about this guy? Yeah, that would be our leaving group. So in this case, we could pop this off. If we pop it off, now all of a sudden we've got this guy floating around in solution, and I'll draw the lone pairs here. And over here we've got this floating around in solution. Got some methoxide where this is fallen off. Which one's more stable as a leaving group? The one on the left or the one on the right? The left. So in this case, this one's going to be more stable. Why? Resonance. Exactly. This is more stable due to resonance. All right, if we're going to look at this reaction, let's just, for the sake of argument, box out this one. Is this one likely going to do SN1 or SN2 chemistry? Let's take a look at the electrophile. The electrophile is the thing attached to our leaving group, so it's going to be this atom right there, right? That carbon with the blue star. I'll make it nice and blue. There we go. All right. So if we think about it, is it primary, secondary, or tertiary? Tertiary, which means is it going to do SN2? No, its backside would be way too blocked for an SN2 reaction to occur, so this would do an SN1 reaction. In either case, though, we can assess the leaving group stability. So let's make a little note, too, that leaving group stability is directly related to the stability of conjugate bases. I don't know if you noticed, but what we're really drawing were pseudo-conjugate bases. So if we've got a stable conjugate base, this means that we've got a good leaving group. This is the overall trend, and luckily we've had a lot of experience with this from our acid-base chemistry chapter. What were the list of roles we did to determine stability of conjugate bases? Yeah, we started with the atom, so we looked at electronegativity and atomic size. After that, what did we look at? Resonance, and then after that, induction, and then after that, hybridization, right? So those same rules apply to analyzing the stability of your leaving group. So if we look at just a simple pKa table, we could say, all right, HI has a pKa of negative 11. That means it has a really, really stable conjugate base because it's a super strong acid. And then we can go down to weaker and weaker acids that have pretty crummy leaving groups. So at the bottom, NH2 minus is a really crummy leaving group. Typically things that have oxygen with a negative charge are going to be poor leaving groups unless there's resonance. And then up here we've got better leaving groups. So you can see specifically water makes a really good leaving group. Why does water make a good leaving group?
The conjugate's strong.
It's stable. When you kick off water, it doesn't even have a charge. So it's super happy getting kicked off. That makes a really good leaving group. And then above it, you've got other really good leaving groups. And we've seen a couple of these already. We've seen chloride, bromide, and iodide. So halogens make good leaving groups. And then in our pod a couple days ago, we saw these sulfur compounds that make excellent leaving groups. Why are these so stable? Resonance, right? So we could say, all right, we could take this negative charge, kick it down, we can kick that up here. Or we could say, well, why don't we kick this down here and kick that negative charge up here? We can distribute that negative charge all over the place. So those make really good leaving groups. Yep.
Would it also help the atoms that you're looking at, oxygen and sulfur being in the same family? You've got you got oxygen surrounding it for that charge to be, and they're large.
Yeah, so you could think about the amount of electron density that negative charge has to delocalize through is huge on these leaving groups. So in particular, you've got a few of these. This is called a tosylate. And a tosylate has this entire group coming off of it. If you have a CF3 in that position, it's called a, let me move this over. There we go. This would be called a triflate. And if you've got a CH3, this is called a mesylate. These all make really good leaving groups regardless of whether or not you have that aromatic ring attached or a CH3 or a CF3. They all make really good leaving groups. These down here, we said make pretty poor leaving groups. In fact, we try to avoid these leaving groups if we are doing an SN2 substitution because the rate is so slow and the reaction's so energetically uphill that it's just simply not going to happen under most circumstances. So really, when we pick leaving groups, we try to pick something out of that top list there. Those are good ones to pick. All right, let's take a look at a situation that's a little bit tricky. Let's take a look at this tricky example. All right, let's say I've got ethyl bromide, and I'm reacting this with sodium iodide, where iodide has our negative charge. And then we're going to do a substitution reaction. Will this be SN1 or SN2? SN2, right? Our electrophile is primary. So primary electrophile. That means that we're dealing with SN2 chemistry. And if we think about our products, that means that this bromine will be replaced with our iodide, and we'll be left with Na plus and Br minus. I'm purposely leaving out that reaction arrow, but I'll give you guys a hint. In this case, we're dealing with an equilibrium reaction. Which side of the equilibrium do you think is going to be favored? The left side or the right side?
Left side.
Or do you think we need more information?
As is left side.
What did we just talk about all day yesterday? Solvents, right? If it's SN2, what sort of solvent would we likely want to use?
A polar non-solvent.
There's a lot of mumbling in the classroom. It's going to be polar, right? Because we need to stabilize that polar transition state. Do we want a protic solvent or aprotic solvent? Aprotic. So in this case, let's make an assumption. We'll assume polar aprotic solvent. All right, now the question, if we think about it again, is which side's going to be more favorable? All right, let's take a look at this. Which one's the better nucleophile? Iodide or bromide in an aprotic solvent? Which one? Bromide. So in this case, this would be a better nucleophile. Why is it a better nucleophile in aprotic solvents? Yeah, in this case, bromine's more electronegative. It's smaller. That's the biggest thing when we're looking at a column, is really small molecules tend to be a little less stable, so they're going to be more nucleophilic. Another thing we could consider is over here, we've got a better leaving group. We just said that iodide's a better leaving group than bromide. So in this case, our equilibrium could be best described as being way more on the starting material side than on our product side. So that is something we have to consider when we're looking at these reactions, is both the leaving group and the nucleophile. And we have to ask ourselves what solvent we're running these reactions into. All right? So now let's go down a little bit, and let's talk about solvents again. Solvents come back in this section. And let's review what we covered yesterday. We said that solvents can be used to stabilize or destabilize things. Your starting material, your transition state, and or your products. So the example we just saw, we said that an aprotic solvent will destabilize really electronegative or small anions. So that's a good example of that changing the stability of your starting material. However, we can think about this with our leaving groups too. So with leaving groups, actually let's do LGS, is to stabilize them as they fall off.
LGS is leaving groups, plural.
Yeah, so any type of leaving group, our goal is to stabilize it as it's getting kicked off or falling off on its own.
So you mean the goal is?
Oh, shoot. Oh my goodness, my brain just like gave up on a few words. So with leaving groups, the goal is to stabilize them as they fall off. Sorry about that. I was looking at my notes and not thinking. All right. If we think about stabilizing them as they fall off, do we want to use a polar solvent or a non-polar solvent? Polar solvents. So let's make a note of that. Polar solvents will stabilize leaving group since they have a partial negative charge. This is particularly important for SN1 reactions. So let's take a look at an SN1 reaction coordinate diagram. I've got energy and I've got my reaction. And let's just do our classic example of my generic leaving group. And then we want to go to our product where we now have a nucleophile that's attacked on. How many humps will it take to get from my starting material to my product? 2 for an SN1 reaction. We know this will be SN1 because we've got a tertiary electrophile. So this first hump is going to be rate limiting. And then we've got this little well. And then we've got another hump after that. So we said that this is going to be our activation energy. So I'll label this EA. And we said with activation energies, our goal is to minimize them, to make that hill as small as possible so that they're easier to overcome. So let's consider what's occurring at this transition state. And we said, all right, this leaving group's falling off. It means this carbon's positive. This leaving group's partial negative. But now let's think about the solvents that are around too. Is it going to be best if we have a really, really polar solvent? We said, yeah, but let's think about how it's interacting. Say, all right, we've got maybe a bunch of alcohols around. And And we could say, well, each one of these could really, really stabilize that leaving group as it's falling off, right? So in this case, if we didn't have a solvent that could stabilize it, we'd say that hill would be a heck of a lot higher because it would be much, much harder for that leaving group to fall off in a stable manner. So let's make a note under here. Solvent stabilizes the transition state. Without a stabilizing solvent, so let's say we used a nonpolar solvent, that hill would be much, much, much higher. The polar solvents, particularly ones that hydrogen bond, will stabilize it considerably. Does that make sense? All right. So let's go on to a little bit of a trick. There are some situations where you're just stuck with a poor leaving group. And what do you do? So let's say I've got this example and I've got sodium iodide and I've got ethanol. Will this do an SN2 reaction? Well, I could say, let's try having this iodide attack, and we could kick this guy off, and we could say, you know, maybe this iodide could replace that, and we'd be left with sodium hydroxide. Is that going to happen?
Bad leaving group.
Yeah, terrible leaving group. So bad leaving group. In fact, we know the reality is this hydroxide would just attack right back and kick off that iodide because hydroxide's a better nucleophile. So in this case, this reaction will not occur. We'll put a big fat X through it. And we've got to figure out how to make this reaction work because we're chemists and we like to problem solve. So the trick is we must find a way to convert a OH into a good leaving group. Does anybody have an idea for how we can convert it into a good leaving group? What do you think, Brian?
Well, first step would be to kick off that H. You'd probably want to put some type of acid in it to.
Okay, so your first trick that you thought was maybe we can convert that OH into a good leaving group by throwing acid in. I think that's good. So throw in acid. Simple enough. All right, so now let's do that. All right, so let's say I've got ethanol and I really, really want to make iodomethane. The question is, what acid do I need to accomplish this transformation? Could it be any acid?
No, the conjugate base would need to be less likely to be.
I'll give you guys a hint. We put iodide on. There's an acid that involves iodine. Yeah, hydroiodic acid, right? So in this case, let's say we toss in HI. Let's determine if this reaction would work, and let's draw out the full mechanism. Okay, what's the first step going to be if we treat this with hydroiodic acid? Give you guys a hint too. The fastest reaction in chemistry is proton transfers. So acid-base chemistry is going to beat any other reaction hands down. It'll occur before any other reaction has a chance to.
Hydrogens attached to that OH.
Yep, so acid-base chemistry says our alcohol can steal this proton. We'll kick off iodide. All right, now at this step, we've got iodide around 2. Is this going to have water fall off randomly, or is this going to do SN1 chemistry, SN2 chemistry? What do you guys think the next step will be? So if we look at this electrophile, this is still a primary electrophile. That means it's going to be SN1, SN2? SN2, okay. All right, but look at this now. We've got a good leaving group. We just said previously that water makes a really good leaving group because when it gets shoved off, it's a neutral molecule. So now this iodide can come around, do this backside attack, kick off water. Oop. Now we've got iodine, we've got OH2.
So we said that's SN2, so that's just going to be concerted, right?
Yep, that just means your nucleophile is going to attack at the same time your leaving group's shoved off. So this can work really, really well for certain situations where you can throw in strong acid, convert an alcohol into water, which is a good leaving group, and then the conjugate base acts as a nucleophile. It's a really simple solution. However, this works best with primary electrophiles. We'll talk about this reaction a little bit more when we get into chapter 8, but there's a competing reaction called an elimination reaction, so we have to be careful with this reaction if we do it on secondary or tertiary electrophiles. So that's one trick. I'll show you guys another cool trick too. So that was trick 1. Trick 2 is convert your OH into some sort of OSR group, right? So we talked about the tosylates, the triflates, the mesylates. We said that those make really good leaving groups. So our goal is to convert this OH functional group into either a tosylate, triflate, or mesylate. Let's talk about how we can do that. So for this one, I'll show you guys one of my favorite reagents. This is called Tosyl Chloride. And usually this is abbreviated TSCl. So if you don't want to write out the whole name, or if you don't want to draw it all out, you can just write TSCl. And during this reaction, we run it in a very special type of solvent called pyridine. It's a nitrogen on the bottom there, and that nitrogen has a lone pair. And pyridine is sometimes abbreviated as PYR in your book. And pyridine is just a really nice, gentle base for your reaction. It's not going to do much besides accept protons. All right, so let's take a look at what's going on here. We said that this is a poor leaving group. What we're going to do, though, is replace this poor leaving group, and we're going to change it into some sort of tosylate group. Now, all of a sudden, we've got this excellent leaving group. The good news is, right now, I'm not concerned with you guys knowing the mechanism of this. I do want you guys to know what reagents you would need, though, and Tosyl chloride is the one that you'll see most commonly in the Klein textbook. Really, all you do is you convert that OH into this big, funky-looking leaving group that we know is very stable, because when it falls off, it's resonance stabilized. Now, all of a sudden, if we've got a good leaving group, we can just use a simple nucleophile. So this would be step 2. We could say, well, now let's just use sodium iodide. And the sodium iodide can now do that backside attack and kick off our leaving group. Sorry. You guys will get good at drawing hexagons by the end of the year, if you're not already. And we said that this is our good leaving group. This is a really, really useful transformation. This is very useful for SN2 chemistry. The one where we used acid, that water can fall off in an SN1 fashion, or it can do SN2 chemistry. It's a little less reliable. This tosylation strategy will almost exclusively do SN2 chemistry as long as you've got a secondary electrophile, primary electrophile, or a methyl electrophile for that matter. So we'll do works with primary or secondary electrophiles. Yep.
So I noticed that you don't always put the plus between the two molecules. Does that matter? In the bottom in our products, you have a plus between them, but the top can.
Oh, it doesn't matter if you have a plus necessarily, yeah. So she was just asking, does it matter if you show the plus in between? It doesn't really matter. It's just kind of habit. All right, so we're getting really close. One thing I will say is let's do a little example reaction for this bottom one. And let's say, I don't know, I want to accomplish this transformation where I've got an OH. This looks a little bit like our pod. And I want to get to SH.
What's that double arrow?
That just means there's going to be multiple steps, more than one at least. How can we accomplish this transformation? Let's try to come up with some sort of plan of attack that accounts for how we can do this. So I'll give you guys a minute to work on this, and then try to explain your answer to your neighbor.
Does it have to be multiple steps?
I'm giving you a strong hint that it will be multiple steps. Yep, only that final product, not a mixture of products, exclusively this final product. You might get other inorganic byproducts, but in terms of your major organic product, this is all you're getting. Yep, I want you to account for stereochemistry too. This is going to help you with the pod. The pod's a little bit trickier. Remember too, we've got a crummy leaving group. Bad leaving group. We'll do a little frowny face.
Sulfuric acid.
Remember too, we're only getting this one enantiomer.
So that's the essence. And that's more like the shade than the secondary, and it's almost the same shape for that little carbon. That's like the exact same shape. So for the text, this bulk field control.
It's just going to float around as a conjugate anion, or counter anion, I should say. All right, how many of you guys think you got a good plan? Some shaky thumbs? You guys want some help getting started? All right, let's take a look at this. We've got a crummy leaving group. We've got to fix it. In this case, it's coming off a secondary carbon, so should we just slam it with acid? Maybe not. There's a more elegant way that we just talked about, and that's where we use Tosyl Chloride, so TSCl. And what was the solvent we used? Pyridine. So PYR. All right, if we do that, now all of a sudden, we've got this leaving group where we've got OTS. You can draw it either way. You can say, you know, maybe I'll draw the whole thing out and I'll say this is the exact same thing. However, what I notice is students quickly get tired of drawing this and they would much, much rather write OTS. Either one's fine with me. All right, so I'm just going to erase that. All right, and now what we need to do is we need to figure out how to get this final product. What reagent would we need? We already had pyridine in the first step. We've created our tosylated product. Now we've got a good leaving group. What should we throw in?
Some type of sulfur compound.
Yeah, some type of sulfur compound. In this case, we want it to be a good nucleophile because it's likely going to be SN2 chemistry. We said tosylations are really good for SN2. So we need to pick a nucleophile that's strong. We need it to be an SH nucleophile. So we could just say, you know what, let's throw at this compound SH minus. And we can't just ever buy a bottle of an anion, so we'll throw in a countercation. So we'll throw in NaSH. All right? What sort of solvent would we like to use? Polar protic, polar aprotic? Yeah, polar aprotic. Does anybody have an example of a polar aprotic solvent we could use? Acetone. Easy enough. So we'll say, you know what, we'll run this solvent as acetone. And then all of a sudden we can say, you know what? Now this can attack, kick off this leaving group. And if you notice, we inverted our stereo center. We didn't get a mixture of enantiomers. We exclusively got our inverted product because we know with SN2 chemistry, we always get an inversion of that stereo center. Does that make sense? What do you guys notice about the pod stereo center?
Retention.
It's the same.
So why couldn't it have done an SN1?
In this case, SN1, we didn't want to occur. We only wanted one enantiomer. We didn't want a mixture of products. So we purposely avoided SN1 chemistry.
But it could have occurred if we hadn't manipulated the solvent.
If we had thrown in H3O plus, a strong acid, we could have potentially had some SN1 occurring too. And in that case, we might also get some other byproducts. And we'll talk about that in Chapter 8. All right, before we leave, let's fill out the rest of our decision-making chart. So we've already done the mechanism, the rate equation, the stereochemistry, the electrophile, but now we've got to fill in nucleophile, leaving group, and solvent. All right, so for SN2, do we want a stable nucleophile or an unstable nucleophile? Unstable nucleophile. So in this case, we want something that is unstable. What about sterics? Do we want it to be bulky or not bulky? Yeah, unstable nucleophile that isn't bulky. That's super important. For SN1, does it matter? Not really. It doesn't impact the rate. All we really need for an SN1 to occur is a lone pair. That's it. So weak nucleophile is okay. It's not involved in the rate determining step. Doesn't really matter. All right, leaving group ability. Which one is it more important for, SN1 or SN2? SN1. So it's very important for SN1. Because it's involved in that RDS, that rate determining step. In SN2, it's moderately important. It's involved in that rate determining step. However, the nucleophile is too. It's not the sole contributing factor in that rate determining step. All right, and then last but not least, for SN2 reactions, what sort of solvent do we want to use? Polar aprotic. And why is it best again? Yeah, exactly. It doesn't stabilize your nucleophile, which means it's going to be more reactive and more nucleophilic. So in this case, polar aprotic works better. With SN1, we said polar protic is actually preferred because it helps stabilize that leaving group when it falls off. And then the other handy feature with SN1 reactions is our solvent can act as our nucleophile. So then you don't need to mix up a different nucleophile and a different solvent. So in this case, we'll say the nucleophile is often solvent. All right, so tomorrow, all we're going to do is practice problems. If you've got problems from the book, bring them. Otherwise, I'm going to have a big list of problems that we'll work on in groups. And then Thursday, I've got a surprise for you guys. A practice quiz. Doesn't count for anything. It's the quiz from last year, so you can see what you might have thrown at you the next Monday, and you can have an idea of what you need to study for over the weekend. So we want to prepare a lot, and then Thursday we'll just do additional practice in the form of a practice quiz.
Like you're going to correct it, or are we going to go over it together?
We'll go over it in class and correct it as soon as we're done.